What's up, science lovers? I'm Makana, one of your cafe coordinators, and we're back with the Teen Science Cafe presentation. Before we go further, we'd like to invite you to subscribe to make sure you never miss out on another awesome NCMNS video. Remember to be respectful in the chat, as our moderators will be keeping an eye on the comment thread, and please leave your questions in the chat. You can check out Teen Science Cafe Raleigh on Twitter, Facebook, and Instagram.
Tonight, we've got an exciting guest for you. Our presenter is Dr. Patrick Troidhart, who is the assistant head of the Astronomy and Astrophysics Research Lab at the museum in Raleigh. His work deals with understanding the evolution of nearby galaxies by studying their different forms and structures. He's here to explain that the Milky Way is not just a candy made of nougat, caramel, and chocolate. Please welcome the star of our show, Patrick.
All right, thanks. Well, let me share the screen here. All right, well, thanks a lot for having me. Yeah, so my name is Patrick Treuthardt. I am the assistant head of the Astronomy and Astrophysics Research Lab at the museum. And I do study galaxies, so I figured I'd talk about the Milky Way, the galaxy we'll probably be most familiar with. But before we do that, I was also asked to talk about my path as to how I got into astronomy and kind of what actually led me to Raleigh, North Carolina. So I grew up outside of Detroit, just north of Detroit in a town called Sterling Heights, Michigan. And there, I mean, we had lots and lots of air glow, so it was really hard to see things in the night sky. But you could see like Orion and the full moon, things like that. But really growing up, I really didn't see a lot of the night sky just because it was so bright. But it wasn't until but basically as I went to school, I knew I was interested in science from an early age. I just didn't know what kind of science. I mean, I was interested in dinosaurs, ants, space, all kinds of things. And it wasn't until high school when I took a physics class that I realized that I was really interested in physics because I liked the math and the fact that you could use math to predict things. Really, you predict the future with math. So I mean, if you knew the velocity and the angle at which you launch a ball, you could predict where it's going to land, for instance. So I thought that was really interesting. And then when I took an astronomy elective in high school, and then I realized it was just physics and space, and then I was sold there. So I knew I wanted to get into that. So I went to public school in Michigan, and then once I graduated high school, I did my first 2 years at a community college near my house. It was literally probably 2 miles away from my house, so it was really convenient. Saved a bunch of money. So I did my first 2 years there, and then I transferred to a school in New Mexico. So I traveled to, I went to school in a small town in Socorro, New Mexico. It's called the New Mexico Institute of Mining and Technology. And it's a really good science and engineering school, and it's really, really small. At the time, it had a student population of about 2,000, and that was with undergraduates and graduate students, I believe. So it was really small. It was out in the middle of nowhere, but it also had the headquarters for the National Radio Astronomy Observatory on campus. So that's what kind of sold me on going there, is because they were really big in astronomy there. So I went there, did my last 2 years there, ended up getting a bachelor's degree, and then I applied to grad schools, and I ended up going to the University of Alabama in Tuscaloosa. And there I worked with a professor who was really well known in galaxy morphology, which is the study of the shapes of galaxies. So he was trying to understand like the shapes and structures in galaxies and what that actually means for galaxy evolution. So I worked with him for my PhD. And after I got my PhD there, I ended up going all the way to Oulu, Finland. And I ended up working with a professor there for a short period of time. And this was my first like postdoctoral job. So I had a fellowship and I ended up working there for a short period of time. So I worked there, and then I came back to the United States, and I came to Little Rock, Arkansas, where I worked with another professor doing the same kind of work, studying galaxy morphology, studying the shapes and structures of galaxies. And I worked with him for a while, for about 3.5 years. And then I got the job at the museum in North Carolina, and I've been here ever since. And so luckily I'm able to, still work on galaxy morphology, still research the things I'm interested in, and I get to talk about galaxies and all kinds of science. So, so pretty fortunate to be here now. All right, but let's talk about galaxies. Let's talk about the Milky Way. So how many people have actually gone out at night and seen the Milky Way? So something like these pictures here, where you see kind of a hazy band of light in the sky. Has anybody seen that? And I don't know if one of the moderators can let me know if people say anything. But yeah, but if you go out into like a dark section of sky, if you go out into like a really dark area, you can actually see the hazy band in the sky. And if you're in a really dark area, you can actually see the color in the band as well. So you can see, let's see if you can see my mouse pointer. So you can see there's some color here and out here, and it's a little more prevalent here in the right picture. You can see it looks a little more orange here in the central region. And you can see there's a dark band cutting through here, and this is actually dust within our own galaxy. And so the bright region that you're seeing is actually billions of stars. They're just so far away that you can't resolve each individual star. So it's basically like looking at cars at a really far distance. Their headlights, the separation between the headlights is so small then that you can't actually resolve them into two separate headlights anymore. It looks like one giant light shining at you. But if you manage to get closer to these stars, you would actually be able to see that they're all individual stars, just billions of stars. And so all that light from those stars is shining toward us, but there's dust between us and those stars, which will block out the light behind it, which gives you this dark band kind of running through the galaxy right here. And that's all dust and gas blocking out the starlight from behind it. So to give you a view, kind of an all-night view of what the Milky Way looks like, this is taken from the Atacama Desert, and you can see this band in the sky right here. I apologize for the flashing. That the video seems to have a slight error in it, but you can see. So here's the band. Here's the Milky Way, and obviously the Earth is rotating, so it's rotating into our field of view. And you can see it looks a little more bluish out here on the edges, and then here's the central region, and again you can see it looks a little yellowish orange there in the middle. And here's just a different perspective where we focus on the Milky Way and you can actually see the Earth rotating. And again, you can see kind of the yellowish orange here in the middle. You can see the dark band of the dust blocking out the light. You can see the air glow from a town out here on the right on the horizon. And you can see planes flying by close to the horizon. But yeah, so that's the Milky Way. So that's, if you go out at night, you might be able to see this if you go into a dark enough area. Okay, so if we subtract out, if we get rid of like all the ground, if we get rid of the horizon, and we take like an all sky picture of the Milky Way, this is essentially what it looks like. This obviously was taken with some high power telescopes, but you could see the Milky Way here. You could see that it looks blue on the edges, out here at the edges. It looks kind of yellowish orange here in the center. And you can see all these dark dust bands kind of cutting through the Milky Way here, all these dust bands blocking out the light. And two other things that you can see here are these two little blobs right here. So there's one down here, and there's one right here. These are called the large and the small Magellanic Clouds. So these are two of the three objects that you can see in the night sky with your naked eye that are not part of the Milky Way. So basically, if you go out in the night sky and you look into the night sky, everything that you see is within our own galaxy, except for three objects: the large and small Magellanic Clouds and the Andromeda Galaxy. Those you can see with your naked eye, and those are galaxies outside of our own. So what you're looking at when you look at the night sky, you're looking at the Milky Way, which is about 200 billion stars. So that hazy band that you see there is about 200 billion stars. So, and there's a tremendous amount of dust and gas in the Milky Way. There's, billions of times or millions of times the mass of the sun. In dust and gas just kind of floating around in our own galaxy. But also, how big is the galaxy? So in order to talk about the size of the galaxy, there's it's so big that it's really hard to kind of really get a good understanding of it. So one way to kind of interpret the sizes of, or the distances between things in the galaxy is to use the speed of light. So light moves incredibly fast. It moves at 300,000 kilometers per second. And it moves so fast that it can travel around the Earth once every 7.5 seconds. So it moves incredibly fast. And it's the fastest that anything can travel in the universe. Okay, so to give you a sense of, for instance, the distance between the Earth and the Moon, so this is a scale model of that. And this is a beam of light traveling from the surface of the Earth to the surface of the Moon and back. And so the distances between the Earth and the Moon are so big that it takes about 1.25 seconds for the beam of light to basically travel between the Earth and the Moon. So it's not instantaneous. It's not like flipping on a light switch in your room, where as soon as you turn on the electricity, all of a sudden the light hits your eye. There's actually a lag between when you turn on the light switch and when that light actually hits your eye. It's just the distances are so tiny that it looks almost instantaneous. But once you start increasing these distances, you can really get a sense of that lag in time, that the light actually has to travel some amount of distance. And so here it's not so bad. It's about 1.25 seconds between the Earth and the Moon, but that is a noticeable lag. What's even more noticeable is if you look at, for instance, the distance between the Sun and the Earth. So when a light beam leaves the Sun, it takes about 8.5 minutes, eight minutes and 20 seconds or so to get to the Earth. So basically, whatever you see happening on the Sun, like for instance, when you go out during the day and you happen to put on some eye protection and safely view the Sun, whatever you're seeing on the Sun actually happened about 8.5 minutes ago. And just because the Sun is so far away from us that it takes that long for light to actually reach us. So for instance, if the Sun blew up, or for whatever reason, it would take 8.5 minutes before we actually see that explosion. So the Sun would already be gone, and we would only know about it about 8.5 minutes later. Okay, so that is the closest star to us. So keeping all that in mind, the galaxy itself is about 100,000 light years across. So that means that it takes a light beam 100,000 years to travel the distance from one side to the other. So the galaxy itself is enormous. It's a very, very large object. All right, so what is the Milky Way? And so there are lots of cultures who kind of studied astronomy in different ways, but it was really the ancient Greeks. So we give credit to the ancient Greeks to really studying astronomy for the purpose of really understanding what it is they're seeing. So a lot of other cultures use astronomy to kind of they used it more as astrology to kind of predict the future in some way, or they used it for determining when to plant crops and things like that. But the Greeks, from what we know about the Greeks, they were really the culture that wanted to understand what it was that they were looking at. They wanted to understand the universe around them. And so we give them a lot of credit for modern astronomy. And in doing so, we also took some of their terms in order to like name some of the things that we see. So one of those is the Milky Way. So in Greek, what they saw in the sky was this Milky Wheel or Milky Circle, which is known as Galaxias Koukulos in Greek, which I'm obviously probably not pronouncing correctly, but they called it a Milky Wheel or a Milky Circle, and from that we get the Milky Way that we call it today. And so they had a myth that that this Milky Circle in the sky occurred because young Heracles was feeding on Hera, woke her up, and then she ended up pushing Heracles away, and then milk spilled into the sky and created this Milky Circle in the sky that we see. And so the ancient Romans, about 1,000 years later, also used the same myth to kind of describe what it was they saw. And so they in their myths, they had Juno and Hercules. Basically, the same thing happened in their story as well. This was about 1,000 years later. But there are obviously lots of other cultures in the world. Everybody's seen the Milky Way, and just depending on the culture, they all have different stories as to what it is that they're looking at in the sky. So actually, one of my favorites is this Finno-Ugaric description of it. And so they called it the pathway of the birds. And this seems to be actually the only one that I've come across that actually has a kind of scientific idea behind it. And it seems to be that this culture, they actually noticed that birds seem to follow the Milky Way in the sky and migrate southwards. And so they thought it was actually the pathway of the birds. They thought that birds actually use the Milky Way to migrate north and south. So I find that to be actually pretty interesting. All right, so like I said, the ancient Greeks were the first ones to really try to understand what the Milky Way was, or specifically. And it was in 400 BC, where there was a Greek named Democritus who had the idea that maybe what we were looking at in the sky wasn't a milky band, but it was actually unresolved stars, and that it was actually stars that were so far away that you couldn't pick out each individual star, that they were so far away that they all blended together and created just one band of light in the sky. And it wasn't until about 2,000 years later that we actually figured out that that's what that was. So technology didn't advance to the point that we could actually figure that out until Galileo in about 1610. So at that time, Galileo, he famously used the telescope to look at different objects, within the solar system or in the sky. So he looked at Jupiter, he looked at Venus, he looked at the sun, and he also looked at the Milky Way. And so he took a telescope, pointed at the Milky Way, and he realized that there were more stars in the sky that he could see through the telescope than with the naked eye. And so what he determined was that what we're likely looking at is unresolved stars in the Milky Way. The Milky Way is made of unresolved stars. So later on, about 100 years later, we were still trying to understand what the Milky Way was, or what it is. And there were two thinkers, two astronomers, who had the idea that maybe what we're looking at is a large disk of stars, that maybe we exist in a large disk of stars, and this is why it looks like a band in the sky. So what is that idea? So for instance, if we're on the Earth and we exist, let's say, in a sphere, and there's stars all within the sphere, if we look outward, outward from inside the sphere, we should see stars kind of scattered uniformly across the inside of the sphere. So what that means is, no matter where you look in the sky, if you're inside the sphere and stars are kind of scattered uniformly in every direction, there should be no preferred direction in the sky where you would look where you'd see any kind of clumping, right? You'd see kind of stars basically everywhere, and it would look kind of the same in every direction. But if you existed in a disk, if you lived in a disk, you'd see more stars in the plane of the disk than you would, looking out, perpendicular to the disk. So what I mean is like you're inside of a hockey puck, and you look along the disk of the hockey puck, you're going to see more stars within that plane of the hockey puck than if you look, outside the plane of the hockey puck, right? If you look straight up or straight down, you're going to see fewer stars than if you look straight through the hockey puck. And so you would see most stars kind of lying in a concentrated band in the direction where the disk is. And you'd see fewer stars outside of that band. And that's actually what we see. So to give you an idea of what we think the Milky Way actually looks like, this is a video created by the European by the European Southern Observatory. And what this is just a computer rendering of what we think the Milky Way looks like. And the video starts and you see what it looks like face on, and then it ends with what the Milky Way looks like edge on. And you can see, as this replays now, you can see that there are spiral arms. There's a linear structure running through the center here. The arms are coming out of the linear structure. But as we turn it edge on, you can see all the dust and gas there blocking out the starlight behind it. And so what we know about galaxies now, like the Milky Way, for instance, these disk galaxies are very, very thin objects. If you imagine taking two DVDs and stacking them on top of each other, that's essentially the ratio of diameter to thickness for galaxies like the Milky Way. So they're very, very thin objects, but their diameters are very large. And all of the material is kind of contained within that disk. Most of the material is contained within that disk. Okay, so now that we have an understanding of what it is that we're living in, what was next, the next kind of thing that people were interested in was, where are we in the Milky Way? Where are we in this giant disk of stars? And so, not too long in the past, for a long time, people thought that we lived in the center of the universe, that we lived in the center of the solar system. But then that was, disproven. We then realized, okay, we're not in a special place in the solar system, that we actually orbit the sun along with other planets. And so we tried to determine where we were in the galaxy. Were we in a special location in the galaxy? Were we in the center of the galaxy, or are we someplace else in the galaxy? So the first person to really kind of try to figure this out was William Herschel in the 1780s. And he figured that if we just start counting stars, and look in every direction and start counting stars, we should be able to figure out where we are in the galaxy. So if we're in the center of the galaxy, when we count stars, if we look in one direction and the other direction, then if we're in the center, then there should be an equal number of stars in one direction and an equal number of stars in the opposite direction. Although if we're at an edge, for instance, we would see all the stars on one side and no stars on the other side. And so if we're somewhere in between, we would expect more stars in one direction and less stars in the other direction. So, basically what he did was he kind of started counting stars. He looked in different directions and started counting stars to determine where we were in the galaxy. And so this figure here is actually the figure that he made, that he drew up and presented in his book. And you can see there's a little asterisk right there in the center, and that's the sun. And all these little dots are the stars that he counted. And based on his little drawing there, you can kind of see that it looks like we're in the center of the galaxy. So we went from the idea that we weren't at the center of the solar system to now the idea that now we're in the center of the Milky Way. And so everybody thought that was a little strange. Why are we in such a special location in the Milky Way? Why would we be at the center? We shouldn't be that special. We shouldn't be that lucky. We should be just kind of randomly placed in the Milky Way somewhere. So the issue was that William Herschel didn't know about the dust and gas in the Milky Way. He didn't know what those dark bands were, and that those dark bands would actually block out the starlight behind it. So for instance, here, when he was counting out the stars and kind of mapping them out, he actually mapped out one of the dust lanes in the Milky Way. He just didn't know what it was. So if he looked above the dust lane and below it, he could count all these stars much further away, but he couldn't actually count the stars behind the dust lane here. So he actually mapped out the dust, but he just didn't know what it was. Okay, so we were kind of stuck with that for a long time. We thought we were at the center of the Milky Way for a very long time. And it really didn't change until the early 1900s. And this happened because of an astronomer named Henrietta Leavitt. So she's one of these like human computers, these people who do computations, who do a lot of math, who's working for an astronomer. And one of the things that she's really famous for is for discovering an unusual type of star. And so this video that you see here on the left is this star. So she was responsible for finding a type of star called the Cepheid variable. And what these are stars that pulsate at regular intervals. And their brightnesses are really well known. So what that means is, so for instance, if a star happens to, one of these Cepheid variables happens to pulsate like once every 5 days, it will have a certain intrinsic brightness associated with it. Okay. If it happens to pulsate faster, like once every 3 days, it will be slightly dimmer. And if it pulsates, like every 10 days, it will be slightly brighter. Okay. So if all of these stars for instance, all of these Cepheid variables, if they all pulsate with a period of 5 days, they all have the same intrinsic brightness. They are all equally bright, okay? And what makes these Cepheid variables really important is this pulsation luminosity relationship. What that means is that if you can see this Cepheid variable flashing, you know, if you can count the period at which it's flashing, you know how bright it's supposed to be, okay? So this makes them something known as a standard candle, okay? So what that means is, so for instance, if you have, you know, a desk full of candles and they're all the same candles and you light them all, right? They're all the same distance away from you. They're all going to look exactly the same brightness, right? Each candle is going to look equally as bright. But now if you take one of these candles and you move it much further away from you, you know that it's going to have the same intrinsic brightness as the rest of the candles on your desk. But now that it's further away, it's going to look dimmer to you, right? Or if you take that candle and you move it much closer, it's going to look much brighter to you, right? But you know that they should all have the same brightness. So if you know that they all should have the same brightness, the same intrinsic brightness, and they're at a different distance and their brightness changes, you can figure out the distance that the candle is, the distance the candle is away from you by just knowing the difference in brightness of that candle, right? So if the candle's brightness decreases by some amount, you can actually figure out that distance because you know how bright it's supposed to be, okay? So these Cepheid variables work very much like these candles. Based on how fast they're flashing, you can figure out how bright they are and figure out their distances. Okay, so they work as standard candles. Okay, so there's an astronomer who picked up on Henrietta Leavitt's identification of these objects. His name was Harlow Shapley, and he said, okay, well, we have these clusters of stars in the Milky Way, these things called globular clusters, and they're kind of scattered randomly throughout the Milky Way. So they're just groups of stars, just kind of bound together by gravity, just kind of scattered randomly throughout the Milky Way. So he thought, okay, well, if we can find these Cepheid variables within these globular clusters, we can figure out how far away these globular clusters are, and then we can figure out how these globular clusters are distributed throughout the disk of the galaxy, okay? And he figured that if they should be, the distribution of these clusters should be centered on the center of the Milky Way. And so what he did was he looked at all these different star clusters, found these Cepheid variables, measured the distances to these clusters, and he was able to determine where we were in the galaxy. And so, for instance, if you look at this middle picture here, all of these magenta dots are these globular clusters, and he was able to measure the distances to them, and he found that the center of the distribution of these clusters was centered around the center of the galaxy. And it wasn't centered around us. So we were actually off center from the center. And so we now know that we are actually about halfway out from the center of the galaxy. That we're not actually at the center, we're about halfway out from the center. Okay, and so by using the same kind of idea, using these Cepheid variables, and some other techniques, we're also able to kind of map out what the Milky Way looks like. So not only do we live in a disk, but we can actually figure out what the structure is within the disk. And so what other astronomers have done was they've looked at groupings of stars, and they found that it's basically not a smooth distribution of stars within the Milky Way, that there are actually gaps. There are regions where there are a lot of stars, and then there are regions where there are very few stars. And what we take that to mean is that that we're actually seeing spiral arms within our own galaxy, within the disk of the galaxy. So we see a bunch of stars where the arms are, and we see very few stars where the arms aren't. So between the arms. So yeah, so this is kind of a map of that. And so this is actually a very difficult thing to do. So mapping out the Milky Way is very much like trying to map out your neighborhood by never leaving your house. If you imagine being stuck in your house and only being able to look out your window and trying to map out all the streets in your neighborhood, it's kind of a tricky thing to do. So you kind of have to be creative about how you do that. And so So what astronomers do is they kind of map out what they can. And then there's a region here, for instance, in this little cartoon diagram, you can see this grayed out region here, and this is actually the shadow of the center of the galaxy. And so we cannot actually see what's behind the center of the galaxy. But we assume that these arms kind of continue along, that nothing drastically changes on the other side of the galaxy. So we kind of interpret what's happening on the other side, and that these arms kind of continue along. And so this is a little more scientifically accurate artistic rendering of what we think the Milky Way looks like. And again, the Milky Way is so big that we can't actually get outside of the Milky Way to actually look back at it. 100,000 light years is a tremendous distance. And so we can't actually get above the disk of the Milky Way to look down onto it to see what it looks like. But we think this is what it looks like. You can see that there are spiral arms here. We think we're right here, about halfway out. Right here's the sun. We think there is a linear structure running through the center of the galaxy that we call a bar. And yeah, it just has a bunch of spiral arms. So these are images of other spiral galaxies that we think look very much like our own. And so you can see, again, here's a bar-like structure. You can see a ring surrounding the bar. You can see these spiral arms coming out of the ring and the bar-like structure. And the same thing is here. You can see a bar, you can see a ring, you can see these spiral arms. So we think our Milky Way looks similar to one of these types of galaxies. All right. So where does the Milky Way come from? That's actually a good question. We don't actually know that yet. What we do know is that early in the universe there was a Big Bang, and then about 4 million years after the Big Bang, the first stars started forming. So that's about right here. Oops, that's about right here in the timeline. So you get the first stars forming about 400 million years after the Big Bang. And really at about that same time, we start getting the first galaxies. The first galaxies start forming about the same time as the first stars formed. And these galaxies formed through a process known as hierarchical merging. And what that means is basically you have small clumps of material that kind of bunch up, and then those little clumps of material are attracted to each other by gravity. And so they get attracted to each other and they collide, and then they form a larger clump. Okay, so then this larger clump is attracted to another smaller clump. That clump falls into it, makes a larger clump, and so on and so on. And then you start getting these larger and larger clumps that become eventually giant pinwheel galaxies like the Milky Way. And that's essentially hierarchical merging. Okay, so this video here kind of shows that process. So you can see there's gas and dust kind of distributed within this field of view. You can see these clumps already kind of forming, being attracted to each other by gravity. You can see that they start to merge, start to collide with each other and merge. They're throwing out more dust and gas. But you can see that they're also spinning. And the spinning is important. The spinning is what causes the spiral structure to form and that disc-like structure, the disc-like shape to form. Okay, so these are very early galaxies now. And you can see that they start to merge and form larger and larger structures. Okay, and you can already see that this galaxy is getting much bigger now. You can see the spiral structure forming. You can see it's spinning really quickly. Okay, so here comes a major merger. And you can see these two galaxies will actually collide and merge together to form a larger structure. And it takes in all that dust and gas, creates a very large disk. And eventually you end up with something that looks very much like the Milky Way. And this is how we think that galaxies like the Milky Way form early in the universe. It's through this process known as hierarchical merging. Okay, and so finally, so what is the fate of the Milky Way? Well, what we know is that the Milky Way and our next nearest large galaxy, the Andromeda galaxy, are actually on a collision course with each other. So we know that these two galaxies will actually, sometime in the future, collide with each other. So they're actually on a collision course. So this simulation shows what will happen when these two galaxies merge with each other. So the Andromeda galaxy is also a spiral galaxy. And when these two galaxies interact, they're going to throw a bunch of stars, dust, and gas out into space when they make their first pass. And eventually, these two galaxies will kind of settle in and form kind of a featureless, structureless type of galaxy known as an elliptical, where it's just a bunch of old stars, no real dust and gas anymore, no more disk. It's just going to be kind of a featureless ball of stars. And this is what we think the eventual fate of the Milky Way is going to be. All right, so what's that going to look like from Earth? So this top left photo that you see here, this is actually kind of what the night sky would look like in a very, very dark area if you took a long exposure. So here you have the Milky Way, and this little blob that you see up here to the top left, that's actually the Andromeda galaxy. So in about 2 billion years, the Andromeda galaxy is going to get much closer to us, so it's going to be much bigger in the night sky. Here it is at 3.75 billion years. And then about 3.9 billion years, that's when crazy things start to happen. That's when the merging starts to happen. And so that's when you get all of these stars, these giant gas clouds, all starting to collide with each other and starting to merge and things like that. And when these gas clouds collide, you're going to get new stars forming. So the night sky is actually going to light up. It's going to be really, really bright with new stars being formed in the night sky. So here it is at 3.9. You can see, again, all the star formation. See these bright blue stars here, these pink gas clouds all over the place here. And eventually things are going to settle down. So just like in the simulation, you get that first pass. And here's Andromeda moving further away from us briefly. Here's the Milky Way being greatly distorted. And here we are merging back together. And at about 7 billion years, basically the night sky is just going to look like a giant fuzzy ball, where our own galaxy is just going to look like a giant fuzzy ball in the night sky. There's going to be no more structure. There's not going to be no more dust and gas. Just going to be old stars just kind of fading out into nothingness. All right, so that's it for the talk part of this. That's all I have for the talk right now. So if you guys have questions, I think we want to wait until the very end to do those.
We can do them right now.
Okay.
Thank you, Patrick. The floor is now open for questions. Please place your questions in the chat or add us on our social media accounts, and we will try to get as many questions as we can. All right, we have our first question. It's by Evelyn. She says, what did you do to pursue astronomy in high school when you couldn't see the sky as much?
Yeah, so that's a good question. So the good thing about astronomy is that you don't necessarily need a telescope to do stuff. Like other people have telescopes and other people have a tremendous amount of data. But for instance, like in high school, like we didn't do a lot of that. We didn't do a lot of like researchy type stuff. We just, kind of learned the basics. And so I was fortunate enough to have, that high school elective class of astronomy that was, I think, a semester long, which kind of just gave you like a little bit of like a base level of knowledge of astronomy. But I also took physics. So I also took the physics classes that were offered in high school. And those are incredibly useful because what a lot of people don't realize by taking like introductory astronomy in college, for instance, is that astronomy really is physics. People think, oh, I'm just going to learn about constellations and, I'm going to learn about, stars and things like that. Yeah, but there's a lot of math involved in astronomy. So it's really physics in space. So I was fortunate enough that in high school, my high school physics teacher was actually really good, and he knew I was interested in astronomy, and so were like some of my other friends in high school, and we would just bug him with questions all the time. And he was actually really nice about it and would answer our questions and gave us books to read and things like that. And I think at one point we actually had a annular solar eclipse pass over where we lived in Michigan, and he actually brought out a telescope for our class to go out and look at it. So that was pretty cool too.
Wow, that is very cool. Good civics teachers.
Yeah.
Make a difference.
Yeah.
Our second question is from Alexa. Where does the name Milky Way come from? Is it purely because of the way it looks?
Yeah, it's I mean it's basically because of the way it looks, but it's also based on the mythology, right? So like if these other every culture has a different myth as to what that hazy band in the sky is, right? For whatever reason, we've adopted the myth that was put together by the ancient Greeks, and so the Greeks thought it was actually a band of milk in the sky. That their myth said that it was actually milk in the sky, and so they then called it that. They called it the Milky Band or the Milky Circle, and that has just stuck for whatever reason. I don't know why. Through history we've decided to keep that, but I think it's just for whatever historical reason. The Greeks went out over every other culture for that reason.
All right. Our next question is by Matthew. What makes the material in the galaxy stay in a disk? Is it centrifugal force against the force of gravity?
Yeah, that's basically what it is. There's so much material in the galaxy that you have a tremendous amount of gravity, right? And it's basically all that material is orbiting around the center of the galaxy. So it really is like centripetal force or angular momentum and gravity working in different directions. And so it just kind of keeps everything in orbit around the center of the galaxy without any external forces disturbing it. That's what ends up happening.
All right. Our next one is by Alexa. What will happen to the Milky Way in the future? Will it ever be destroyed by an unknown factor?
Yeah, so we do think that the Andromeda Galaxy is going to merge with the Milky Way. So the Andromeda Galaxy is a disk galaxy that's as big or bigger than the Milky Way. And so both our galaxy and the Andromeda Galaxy are on a collision course. And when they once they get close enough, then the gravity between the two galaxies will actually start to pull on each other, and they'll start to merge together. So then you have all that dust and gas will start to collide. The stars will be scattered all over the place, and eventually those two galaxies will actually merge into one single galaxy, one larger single galaxy. But all that dust and gas will form new stars, and those stars will burn out very quickly, and there will really be no more dust and gas left. And so you won't end up with two disks anymore. You'll end up with basically a giant ball of stars with no more dust and gas in it, so no more stars are being formed. But you just end up with a ball of stars that are just slowly burning out. So nothing. I mean, it'll be exciting in the very beginning, but toward the end there, when things kind of calm down, our galaxy is just going to fizzle out.
All right. This question is about the photos that you showed us before. Mm-hmm. They're asking what makes the different colors of the Milky Way.
Yeah. So right. So that's actually good. Let me go back to this slide. Well, so a little bit of this is Photoshop to kind of enhance the colors. These are the best photos I could find that kind of show the natural colors a little better. But again, they're still slightly enhanced. So if you go into an incredibly dark region, for instance, I've been to the Big Island of Hawaii and been in a very dark region of the Big Island of Hawaii, and that was the first time that I've ever seen color in the Milky Way. Usually when I see the Milky Way, it just looks like a very faint band in the sky. It's hard to see anything other than a little bit of white. But if you go into a dark enough area, you can actually see some of the color. And so in the center of the galaxy, so actually, wait a minute, let me actually switch this to this slide. In the center of the galaxy here, it looks a little more yellowish orange. than if you look along the edges out here. On the edges, it looks a little more blue. And what that is the differences in the stars. So when you're looking out here, you can see also it looks a little bit thinner out here at the edges than it does in the center. The edges out here, that's the actual disk of the galaxy. That's the far outer edges of the disk of the galaxy. That's where the spiral arms are. And where the spiral arms are, that's where you get a lot of star formation. And when you have a lot of star formation, you get a lot of really blue stars. And these blue stars burn out quickly. So when you have star formation, it'll create these blue stars that'll burn out quickly, but it'll keep creating them. So, and these blue stars are much brighter than the reddish orange stars. But when you look toward the center of the galaxy, you see a lot more of these reddish orange stars. So there's not a lot of star formation going on there. So you're just left with those reddish orange stars that last much longer than the blue stars. And so that's why you kind of get that color difference. So it's really just different types of stars, just some overpowering others, and then some burning out and some not.
Interesting. Our next question is, why does it take 5 months to tweak the James Webb Telescope when it arrives in L2? How can this take so long?
Well, so yeah, the James Webb Space Telescope, it's the whole thing, everything with the James Webb Telescope is really methodic, in that they really want to be sure that everything works correctly and that they don't break anything. And so they do everything slowly, everything deliberately, everything very, very carefully, because if anything breaks, there's no way to fix it. And so, you know, they've been building this James Webb Space Telescope for a very long time, and it's taken longer than they expected. It's taken much more money than they've expected. But, you know, now they finally launched it. Everything's been successful so far. And, you know, now it's taking about a month to actually get to the location it's supposed to be at. But this location is so far away that it can't be serviced by people. So if something tears, if something breaks, if something rattles loose, there's no way to fix it. It's just gonna sit there broken. So everybody wants to be really careful about, you know, unfolding it. You know, it's basically like unfolding tissue paper. You know, you want to be careful and not tearing anything, because there's no way to like go out there and like tape it up, right? So you just want to be very careful about everything that you do.
All right. So how do we know that our galaxy is barred, spiral, and not normally spiral like Andromeda? Did that make
Andromeda,
sense?
yeah.
Andromeda, I'm sorry.
No, that's a good question. It's hard to figure out. But what we do know, where is that? So one thing that we do know, so if we show this video, so these barred spiral galaxies, one of the interesting things is that if you look really closely at a barred spiral edge on, sorry for the flashing, but you can see this X-like structure when you look at this kind of edge on, running through the center there, that X-like structure, and you can see this little dimple right here. Oops, I gotta let it play again. But you see that little bulge, you see that dimple in the bulge, and then you see that X-like structure, that faint X coming out of that bulge. Those are indications of a bar. And so what astronomers can do is they can look for this X-like structure, and they can look for that little dimple, and that can tell us whether or not the Milky Way is actually barred. Now, obviously, you can't really see it in this picture, but you know, if you know, obviously, astronomers are doing a lot of research on this, you know, trying to figure this out. But what you look for is, you know, the orbits of these stars. You look for, you know, what the structure kind of looks like, and there's a lot of evidence to suggest that we actually live in a barred spiral galaxy. The weird thing is actually, if we go to that other slide, if we look at this diagram here, so we have this long bar right here in this drawing, but we also have this wider bar over here. What the data tells us, what the data is telling astronomers, is that the Milky Way actually seems to have two bars. We have this long, narrow bar, and then we have this slightly shorter, slightly wider bar as well. That's a little off from the other one, and that's weird. All the galaxies that we look at, no galaxy we've seen has two bars like this. but the data is telling us that that the Milky Way actually has 2 bars. So it's not known if one of these sets of data is wrong, like one of these bars actually doesn't exist, or do we actually have 2 bars? It's hard to know. Again, we're inside the Milky Way and there's no way to get outside of it. So it's hard to look toward the center of the galaxy and actually figure out what's going on. It's much easier to look at a galaxy outside of our own and say like, oh yeah, that one definitely has a bar. That one has 1 bar. Yeah. So it's a lot trickier to do it in the Milky Way than it is for other galaxies. So in my opinion, I don't think we have 2 bars just because I don't know dynamically how that could be sustained. But so far the evidence suggests that we have 2 bars. So who knows?
All right. So how long does the process of galaxy merging take approximately?
Well, I mean, yeah, it depends on the galaxies, their velocities, things like that, the masses of the galaxies. But once they approach each other and they're not moving very fast relative to each other, once they start to feel each other's gravity, it probably doesn't take very long, in the overall grand scheme of things. So for instance, the Milky Way and Andromeda, I mean, once it gets to its relaxed state, it takes about 3 billion years, which, sounds like a long time, but really in the whole life of the universe, which is like 13 and a half, it's not that long. But, the merging process starts at about 4 billion years from now, and then, it's pretty much done at 7 billion years. So, for human lifetime, for the entire existence of humans, we won't be around to see this, and we won't see it to the end either. But for the lifetime of the galaxy, it's pretty short.
Okay. So you say that stars will collide when the Milky Way and Andromeda merge, but isn't the chance of that happening still very astronomically low? Would the Earth even exist at this point? What would happen?
Yeah, that's right. So when the galaxies actually merge, the stars themselves will not actually collide with each other, because while they have a lot of mass, their diameters are very, very tiny to the amount of gravity that they have. So their mass is not spread out over a large volume. They're actually very small volume objects. And so when 2 galaxies merge, the stars will actually feel each other's gravity, and they'll kind of be scattered out because of gravitational disturbances. But the chance of any 2 stars actually colliding is super, super tiny. But what will happen is these giant gas clouds within the galaxies, they have a lot of mass but spread over a large volume. And so these gas clouds can actually collide with each other. And when they do, when 2 gas clouds collide, they'll compress and form like shock fronts, for instance. And when they compress, they'll collapse and form new stars, where they end up collapsing. And that's when you get new stars kind of forming and things like that. So yeah, the stars themselves, the chances of them actually colliding is very, very tiny, but the gas clouds, the chances are actually pretty high.
All right. What causes the band to form and remain intact in the spiral galaxies themselves?
Yeah, so that's actually the conservation of angular momentum. So what that is, so if you're not familiar with that, like in high school physics or something like that, if you have like a swivel chair, wherever you're sitting, if you kick out and you have to move like way out. I'm not going to do it, but if you move way out and you stick your feet out and you swing around in a circle, right? You're going to swing around in a circle, but then as you bring your feet in, you're going to actually spin around faster. Okay. And so that's angular momentum being conserved, right? So rather than having all that mass spread out over a large volume, over a large distance, you bring that mass further in, you're basically going to end up speeding up. Okay. So similar things happen in galaxies, in that if you imagine a galaxy starting out as just a ball of gas that's slightly rotating, So it's got a little bit of angular momentum. So what will happen is gravity will actually cause the poles of that gas cloud to drop down. And as it does that, and it'll pull in a little bit. And as it does that, it'll actually speed up. And it'll actually start to spin a little bit faster. And so basically angular momentum is being conserved. And so what will happen is that the edges of the disk will kind of stay further out, but the poles the edges of the gas cloud will stay further out, but the poles of the gas cloud will actually fall in, and then you end up with a disk that's being sustained by the spinning.
That was a great explanation. That made perfect sense with the chair. So what has been one of the most awe-inspiring moments that you've had when studying galaxy morphology?
Oh man, that's a good question. Honestly, the coolest personal thing that I've ever come across was really seeing the color in the Milky Way, with my own eyes. Because a lot of the work I do, I use images that have already been taken by telescopes, and the images I get are black and white. And that, we take an image of a galaxy, but it's not like a full color image. We take images that are just like a narrow wave band, right? So it's like a small range of wavelengths. So we just look in the infrared, or we just look in the blue, or we just look in the green, because each one of these wave bands gives you different information about the galaxy. It tells you something different about what's happening in the galaxy. And so you can stack those on top of each other, and then add false color to it and kind of make it look realistic. And so you get a kind of a sense of what the galaxy looks like in real life. But to actually see the color in the Milky Way itself with my own eyes, that was really cool. Just because I know so much about galaxies, that being able to see the orange in the central bulge region of the Milky Way, and then the bluer outer regions, in the disk, that was pretty impressive. Being able to actually see real color in a galaxy, that was neat.
Sounds amazing. All right, last question. Is the Milky Way impacted at all by climate change? And how can we as Earthlings be better stewards of our galaxy? Asked by Kristen.
Okay. So the Milky Way itself as a structure is not impacted by climate change, but our view of it can be. So part of the issue is that with climate change, some of the problems that arise with that is increased humidity. And so with increased humidity, so for instance, if you want to take a telescope out at night, if the humidity is really high, you're looking through not only the atmosphere, like all the air and the dust and everything that just happens to be in the air, but you're also looking through all the water vapor in the sky as well. And so if the humidity is really high, and you happen to live near a town or whatever, you get a lot of sky glow. So I'm assuming most people, in this talk have, lived near Raleigh. And so if you've ever driven by RTP at night in the summer, you can see these greenhouses that are just glowing like super bright. And that's especially in the summer when it's really humid out, you can really see like this tremendous air glow from these greenhouses. And so humidity actually, it will affect your visibility of the night sky as well. And it can affect, your view of the Milky Way from the ground.
All right, thank you guys for asking so many wonderful questions. We do apologize for not being able to get to them all. Thank you again, Patrick, and thanks to you all for watching. I hope you're amazed by everything you learned today. We would also like to thank the museum's digital media team for helping put on the cafe. Don't forget to follow the Teen Science Cafe and mention us on Twitter, Facebook, and tag us on Instagram. Check out the QR code on screen or use the link in chat to complete our survey. The survey will also be sent in a follow-up email that you are registered with. Completing the survey enters you in a drawing for a $10 e-gift card of your choice to Amazon or Starbucks. Be sure to complete the registration form and tune in for next month's cafe on Friday, February 4th at 6 p.m. If you're interested, be sure to stay tuned for details.
Thanks for joining tonight's Teen Science Cafe. Make sure to hit the like and subscribe button and hit the bell notification to make sure you don't miss any premium content from the NC Museum of Natural Sciences. Don't forget about filling out the cafe survey because your feedback matters and you'll be entered into the gift card drawing. My name is Rayon and these have been your cafe coordinators. Stay safe this January. See you later, Space Invaders. We hope you have a stellar start to the new year and we can't wait to see you next month.